Good afternoon, everyone. I'm James Hunt, and I'd like to present my thesis, Quantifying the Isocentre Accuracy of an Elekta Unity MR-linac through full gantry rotation. I'd like to acknowledge and thank my supervisors, Pejman and Martin, who are here, and Hans in Denmark. So I'd like to introduce by just talking quickly about target volumes. Most of you probably know a bit about them. We have a gross target volume in a tumour when you're looking at treating a patient. Gross target volume is the visible or through imaging portion or volume of the tumour. You then have a clinical target volume because when you can see a tumour in a patient, you assume there is some subclinical invasion as well around the tumour that you want to treat. You also want to treat an internal margin, an internal target volume to account for the patient moving, especially if the patient has, say, a lung cancer and they're breathing, there's going to be some movement involved. Also, there's going to be a setup margin. So every time the patient is set up, cumulatively, this creates your planning target volume. And that's what gets targeted by radiation therapy. You also want to avoid certain areas known as organs of risk. Here is an example of a breast tumor. So you can see in this patient, they've circled a sort of planning treatment volume of the whole breast, because there's they've also highlighted the organ at risk, which is the heart here in the center of the chest. Obviously, you don't want to go radiating a heart unless you really have to. So a breast can be reasonably easy with IMRT, which I'll describe in a bit, to target without hitting the heart. When you get to organs such as the prostate, it becomes a bit harder to target due to the amount of organs around. So you've got organs of risk in the femur head on either side you don't want to dose. You've got the rectum and the spine and the bladder all surrounding the prostate. So we've developed, medical physics has developed new technologies to increase target accuracy to the areas such as the prostate, but sparing the organs at risk around. So I've got some examples of image-guided radiotherapy modalities here. You've got 3D conformal radiotherapy here, quite a basic one where they've just targeted from 2 directions or possibly 4 directions. I would say probably 4 directions, I think, but don't quote me. So you can see they've hit the femur heads with a bit of radiation, but most of the radiation, like the highest portion of radiation, has gone to the prostate area. IMRT, its specialty in IMRT, you use a multi-leaf collimator to adjust the shape of the beam as well. And you also target from chosen angles. So here, potentially, they've targeted from 3 angles, and they would have modified the beam. So rather than just having to increase the focus to the prostate while sparing around the prostate. VMAT is sort of the next development from that. You're targeting in arcs, so a full arc around the prostate would be used, and the multi-leaf collimators would be used to adjust the size throughout that gantry rotation. So you can see now at this stage they're getting a really focused high dose area around the planning target volume, but sparing a lot of the surrounding areas. The next step forward from this is stereotactic therapy, which does use VMAT or IMRT technology often in its rotation, but they have much higher precision, so they're accounting for patient movement a lot more. And you are using a higher dose per second and advanced imaging technologies, so you get a much more conformal dose. So if you look at sort of VMAT, you've got a lot of dose around. Stereotactic, wrong button. Sorry, you're looking at focusing on that area. You can see here a dose volume histogram of stereotactic therapy, where you've got the planning treatment volume receiving a high dose. The femur heads, the rectum and the bladder are all getting a much lower dose throughout treatment, which is what you're aiming for to increase your therapeutic ratios. What can we improve on this? So traditional RT, you're accounting for organ movement, setup error, as I mentioned, and organs at risk. This is all based on pre-radiotherapy imaging. So you take a CT scan of the patient, do some, I forget the word right now, pre-simulation. So you do a simulation of that treatment based on imaging done before you started treatment. But as you can see, with this study, they found that by fraction 9, a stomach had moved up to more than 5 centimeters. So there are some errors there involved, that, as Ghazli mentioned as well, basing your treatment purely on pre-radiotherapy imaging. Adaptive radiotherapy is sort of the next stage of development. where you start looking at interfraction changes in your treatment plan and intrafraction changes in your treatment plan. So whether you're so you might image between fractions and or during fractions. So this allows you to increase dose again to the planning target volume. The volume's position can change through treatment, and you're getting more precise aim to the target and missing the organs at risk when you don't have to hit them. So I put in a little funny comic here because Pejman said I should have a bit of humor involved. So some surgeons going in, but they clearly are vision impaired. You wouldn't want to have surgery without vision. That leads me to radiotherapy. If we have a CT beforehand, but then you're not able to see what's going on, you might think that's a bit like this situation. We're a lot better than that, but MR-linac is what I'm trying to get to. So MRI-guided radiotherapy is, in particular, using the Elekta Unity, has the ability to use MR imaging during treatment and during fraction delivery to get a really good view of what's going on. And generally it consists, I'll show you some images later, of a linear accelerator coaxial with an MRI imager. So here's some examples quickly of MRI and CT, some basic differences. CT, and so you can see the difference in soft tissue contrast is a main benefit of MRI. So you get a much higher definition soft tissue contrast and different options for imaging with MRI. CT does have other options as well, but MRI is known for its soft tissue contrast. Another main benefit is there's no imaging dose with MRI as opposed to CT. As I mentioned also, you can have real-time imaging for ART. So in Denmark, Hans told me all about their treatment plan, their daily sort of treatment. They have trialed either adaptive position radiotherapy, where they keep the target volume shape the same, but they move it based on their imaging of the target. They also have adaptive shape volume targeting, where basically each day they're imaging the target volume, they are adjusting the shape of their treatment, and then they're targeting. So that one takes longer to compute, though the patients reportedly all tolerated that time really well. So there are options for intrafraction treatment, as I mentioned. The negatives of MRI, there are negatives for its use in RT. There's an electron return effect, which I'm about to address. MRI has image distortion, which I'll show you an example of in a second. A big thing is that there's no Hounsfield units with an MRI. So when you're planning with a simulation based on a CT, CT is radiation which is absorbed in the same way as you would. It's slightly different to an MV beam, but like KV and MV are both photon radiation and absorbed in a similar fashion. And you can use that to plan where the dose delivery. You don't have that with MRI images based on proton position rather than electron density. So I mentioned electron return effect. It's just an interesting, reminding me of undergrad physics. But as you're getting X-rays passed through a patient or a phantom, if they're converted to electrons, those electrons then might leave if they're near the edge of the patient, and then they're just continuing a straight line if there's no magnetic field. When there's a magnetic field, and especially a strong one, those electrons are caused to spiral by the Lorentz force and can re-enter the patient. So you can see here the gray line is a typical dose distribution you would expect. But with a 1.5 Tesla magnetic field, as we have in an Elekta Unity, there's a much higher exit dose. I mentioned distortion as well. Here's an example of what should be a square field distorted by the non-uniform magnetic field. As much as we try to keep it uniform, you can't. That's very difficult. So that's something that has to be accounted for in treatment planning. So I'd like to talk about the significance and aims of my project. What does Elekta Unity offer? As I mentioned, there's excellent target delineation for your treatment volumes. Highly accurate and precise treatment to target volume is what's offered as well. So you can not only see the target really well, but you'd hope to be able to target the volume really well. But because it's a new technology, there haven't been as many studies into how accurate that is, and that's what my study is about. So my main goals are quantifying the sag of the imaging, the MVIC. In other machines, this is called an EPID. You probably all know the term EPID a lot better. So here's the imaging panel here. I also want to quantify the sag of the radiation head, which is going to affect the treatment accuracy. And I want to present a reproducible method applicable for further studies. I'm only looking at one unity, but I'll talk a bit more about that in future studies. I also want to look at this all through through full gantry rotation. There have been a couple studies that have examined positional accuracy of the treatment beam during at cardinal angles, but not through full gantry rotation. So mine is the first study to examine accuracy to this extent. So just a quick look at past literature. As I mentioned, there's not a lot for MRI guide for MR-linac, but there has been a lot for conventional linac, especially from Pejman. So there's a lot. I won't go through all the numbers here, but I've mentioned the AAPM's recommended monthly QA limits from TG142 are 2 millimeters or less for non-stereotactic and 1 millimeter or less for stereotactic radiotherapy. So that's the imaging and treatment coordinate coincidence that we expect. That's our recommended limits. So you can see for the course of movement for some, I'll explain course of movement in a second. You can see that some regular linacs have exceeded those limits. There are some numbers up there. I just wanted to explain course of movement. I explain that as the distance between the maximum and minimum data points, and that'll make more sense when you see my graphs later. If you're looking at a sinusoidal pattern, that's basically peak to peak amplitude. So that's the maximum movement you'd expect in difference in position. My coordinate system, if you aren't familiar, cross-plane on the imaging panel is defined as being sort of across the patient's body. So sometimes that's going to be vertical as the gantry rotates, whereas in plane is the parallel to the patient's spine is how I like to think of it. That's always going to be horizontal. That's important for my data later, as one of the causes of sag is gravity. In plane isn't affected by gravity as a sinusoidal kind of thing, whereas cross plane is. So my materials and methods. This is a phantom that we designed. Basically, it has 4 ball bearings made of tungsten carbide implanted in a plate. We use 2 different materials for plates. We mainly use reinforced plastic, but we also tried a cardboard plate to see if that would give us better contrast to noise ratio. I've got the dimensions there. Basically, they're rectangle 40 by 15 millimeters. We placed those early in the beam path attached to the radiation head. So you've got the source up the top here, beaming through our radiation head phantom. I'll talk about this superconducting wire in a minute because it was very annoying, and I'll explain why. There was a Winston-Lutz phantom. I hope most of you would know a Winston-Lutz phantom is a phantom held as close to isocentre as possible. We're using that for the MVIC motion, and the imaging panel is down here. These large blue bits, I forgot to mention in the earlier diagram, are the magnets of the MRI. The MRI is within the rotational gantry of the linac. One of the benefits of the linac is rather than having a large, heavy, bulky gantry moving around, it's all attached to the MRI like you would expect a CT, so it can sort of just whiz around. One thing I know it can do, which is very interesting, it can just constantly rotate because it doesn't have brushes attached to wires, it has contacts as it goes around. Here's my drawing of basically our setup in 3D. You've got the phantom here attached to the radiation head, beaming through the Winston-Lutz and creating this image here with 5 dots. So here's the actual images I got when I first started the project. The first data set was taken in February last year. I didn't start until around this time last year, late last year. These images were taken, I originally got 3 full rotations worth of images, taken basically 1 every 5 degrees of rotation, which came to a total of 216 images in each direction, both clockwise and counterclockwise. Late in the project, so only 2 months ago, I got a second data set with 3 times as many images, a full 9 rotations in each direction, and this is where we use the 2 different phantom materials as well. So we use both the plastic and the cardboard. I mentioned the superconducting wire earlier. This is for carrying data and signal through the MRI-linac. I'm not sure its specific purposes, but it gave us these very annoying artifacts, which at times stopped us being able to take data. As you can see, these circles were quite hard to detect, especially for MATLAB, due to these artifacts going here. I spent a lot of my project trying to overcome this artifact with very limited success, unfortunately. So there's some gaps in the data where there is no data for some of the circles. I've mentioned that between 6 degrees and 21 degrees we can't treat. That's because that's the actual angle where you're facing straight onto the conducting wire, and it's hardwired into the Elekta unity that it can't treat at that position, so it treats around that position. And all these images were taken in Denmark by Hans. So the goal of my program I did a big MATLAB program, was the bulk of my time. First goal was to extract the circle positions as accurately as possible from the images. Second goal was to determine the motion of the MVIC panel itself, and the third was to determine the motion of the radiation head. To get that accurately, we needed to subtract because we're using the MV panel for all our data, we need to subtract the MV panel motion from the images to get the radiation head data. So my first attempt last semester was to use a Hopf transform. A Hopf transform basically assigns points to potentials, assigns each pixel to a potential circle based on parameters, and then it counts votes for each circle, and the circle with the most parameters is like the most likely circle. Sorry for that quick explanation. I can explain further later if you're interested. This turned out to be rather inaccurate, as circles weren't clearly defined in these images, and the image is quite noisy. And I was finding a precision, at best I would get like 2 to 3 pixels, which was quite a lot for what I was aiming for. It also had a lot of trouble dealing with these artifacts, and that created, like you can see here, kind of looks like a circle even though there's none there. Hopf transform was picking up a lot of things like that. So as I mentioned, noisy images, circles weren't well defined. I addressed that through image filtering. I tried a lot of different image filtering techniques. Imaging artifacts, there were less clear solutions. As I mentioned, I ultimately couldn't really resolve those in the scope of my work. So different filters I tried. The main ones were the Gaussian filter, Wiener filter, median filter, max filter, and minimum filter. And I tried these with mask sizes of 3, 5, and 7 pixel squares. Each of these filters is a spatial filter. Basically, it looks at a certain pixel and the neighborhood of pixels around it in the mask size. If it's a median filter, for example, it'll take the median value of that neighborhood and assign it to that central pixel, and then that repeats that for every pixel. So max and min are the same. Wiener is a bit complicated. I'll get to that in a second. Gaussian is also known as a smoothing filter. It doesn't use a mask size. It uses a sigma. If you know the shape of a Gaussian function, it peaks in the middle and then drops out to either side. I couldn't put one in, sorry. So basically it gives the assigned value to a pixel is most defined based on the central pixel, and then to lesser degrees the pixels around it. So the further the pixel is, the less it influences the final value, but that causes a lot of smoothing. Wiener filter was a very complicated one. I haven't given a full explanation here because it takes quite a while to explain. Basically, it looks at a standard error function, and it minimizes that, and this line here is the solution to that statistical error function. It looks at the local mean around in the neighborhood of each pixel and the local variance, and tries to minimize the statistical error function value. Also, alongside my filtering, to get better after filtering, rather than just using a Hopf transform again, you develop this technique where you take 5 profiles through each circle, both vertically and horizontally, so 5 lines of brightness values. You average them together to get like 1 horizontal and 1 vertical average, which eliminates a lot of the noise. This isn't an actual line, this is just one I've drawn. What we did then is take a minimum brightness that we detected and maximum brightness, average those to get 50% brightness. I fitted a cubic curve to each side of the brightness value through 4 points around that value, and took the intersection, as I'm demonstrating with the pointer, the average sub-pixel value between those positions we classed as the center. That proved a lot more. Just quickly, step 2 and 3 that I mentioned, the actual SAG. These were much more simple to compute than all the mathematics of the filtering. The MVIC SAG, we used the Winston-Lutz phantom. We removed the first harmonic component from the cross plane to account for any changes there. We also removed constant shifts from both of them. The radiation head sag, if you remember my phantom, it had 4 ball bearings. We took the average position of the average position of all 4 bearings. We subtracted the MVIC sag, and that gave us our radiation head sag. We repeated this for each filter for comparison. So this was a relatively simple code, but there was a lot of code to implement in. I learned a lot about data processing with MATLAB, which was very interesting. My results and discussion. For my results, I'm sorry it's cut off some of my, I think you can guess what all the filters are there. The filter I ended up choosing was a 5x5 Wiener filter. It had very high success in detecting circles. They all have rather similar contrast to noise ratio, because noise, I didn't boost the contrast between each. They all had the same sort of treatment to boost contrast, which doesn't affect the detection ability too much. The Wiener filter also had a very low standard deviation, and I'll explain more about the standard deviation in a few slides. So you can see the Winston-Lutz phantom positions here for each 3 data sets. So that's the initial data set is in red, the black data set is with the cardboard phantom, and the blue data set is with the plastic phantom the second time. So you can see that there are 3 distinct setups. They're all oscillating kind of differently in the cross-plane coordinates, which would indicate that there's a slight misplacement in where that ball bearing is in the isocentre. Whereas with the in-plane coordinates, there's just a constant shift, but they're showing a similar pattern. Once you remove the harmonic from the cross-plane data and move them both to around 0, we got much more interesting results. So the cross-plane MVIC sag, basically, you can see there's a high conformity between clockwise and counterclockwise data. I fitted an 8th order Fourier transform, mainly for interest. You can see it doesn't conform too well, even with 8 degrees there. So there's a lot of random movement. In plane MVIC sag as well, we have a lot of movement. There's a little less conformity between both directions here, but they're following roughly the same pattern. I put this in millimeters, so you can see a course of movement of less than 1 millimeter in the less than 0.1 millimeter in the cross plane, and about 0.1 millimeter in the in plane. 1 pixel at isocentre projects to 0.216 millimeters. That was determined during acceptance of the Elekta unity. For the radiation HEG-SAG, once I've removed the MVIC, we got, you can see quite a sinusoidal pattern in the cross plane, and a very high R-squared value for fitting just a first order Fourier, so a sine wave basically, to each of those. What's interesting in this is that there's quite a difference between the clockwise and counterclockwise data. I don't have a solid reason for why that is. I suspect that it's due to the mechanics of how the radiation head is attached to the gantry and how it changes as it goes around in the different directions. I should note as well, this was measured as step and shoot, not a constant shooting. So I don't have a constant. That's why it's every 5 mil. I believe the Unity does have the faculty for arc therapy, but it's not in place yet. They're just using step and shoot. In plane, it's more like 2 straight lines. There's not a very good fit sinusoidally to that. I think it was an R-squared of about 0.5, so I haven't plotted those together. But you can see there's a high conformity in this plane between clockwise and counterclockwise. So just a summary table of my results. If you remember the AAPM recommendations for treatment coincidence, you're looking at 1 mil for less than 1 mil for stereotactic. And you can see in these, the course of movement, the radiation head cross-plane motion was more than 50% of the stereotactic 1 millimeter, which is a significant portion of your setup, of your margins when you're taking into account setup margins and anything else. In plane was a bit lower. But it did perform much better than a lot of conventional linacs. This is an example of the profiles that my program spat out. So you can see, and this is sources of error is what I'm talking about now, sorry. So the superconducting channel, if you remember its brightness, it sort of created a lot of profile going across. When you want a circle, you want a nice symmetric pattern. So I tried to cut the results to get rid of anything not symmetrical. You can see where the circles are here, but the superconducting channel would have thrown results out here. And despite my best attempts to get rid of it completely, it still kind of stuck around. One of the methods I tried to eliminate its interference was to set a limit on the difference between the left and the right values, if that makes sense, expecting a bit of symmetry, but I didn't, there's a bit of interference here. But as you can see, there's a lot of circles here and not so many lines there, so hopefully it didn't interfere too much. Another source of error, how precise was my circle finding process in general? That's what I was asking myself. I attempted to quantify this with standard deviation, which you saw a couple slides back when I was looking at the various filters. The problem is, so what I was looking at is for each gantry angle for each setup, so to eliminating other sources of error, so if I've got 3 rotations in one setup, how widely spread are those data for the same gantry angle? If you assume the same gantry angle is going to treat the same area really precisely, then any error in that would be due to my code picking up the circles differently. Unfortunately, you're not going to get exactly precise every time you're treating the same point. So currently this says treatment precision, that should say targeting precision, radiation targeting precision. I didn't find a way to separate my program's precision from the precision of the radiation beam. So that would be a potential further study. So I want to evaluate my study. The aims I mentioned before were to quantify the sag of the MVIC, which I believe I succeeded with. I had quite tight confidence margins of about 25 micrometers or less. The radiation head sag, I again managed to quantify successfully with a 50 micrometer margin in each of my graphs. I also wanted to present a reproducible method applicable to further study. The method was time-consuming for attaching the gantry to the radiation head. Hans and his engineering team had to remove various access panels. There was no easy attachment point. But after they removed a bunch of, I have the full details of how they did it if you want to ask me afterwards. That's a detriment to this technique is that it was time-consuming, but it was doable. And as we did it twice, over a year apart, it got very reproducible results. I feel like that suggests that this would be a good technique if we wanted to look at multiple unities and get better feedback for more machines. Future work, that's the wrong list of my future work. Future work for this project, not for me. Only one unity has been tested so far. As I keep mentioning, the more unities we test, the better. If the sag is different for each machine, then maybe that's something that machine can take into account for treatment. If there was a universal sort of sag across every unity, and we got that information back to Elekta, they would maybe have a chance to implement something to counteract that during the manufacturing process and increase their accuracy. One study which I found really interesting, Du et al., looked at compensating for sag with MLC using beam shaping, which could be another thing to look at for unities. Speaking of the MLC, one thing I didn't get a chance to do in this project that Hans was hoping I'd be able to do was quantifying the MLC and the jaw sag. The treatment area for this project was quite small to make sure that the edges of the field from the jaws and the MLC were visible. It wouldn't take too much to use the same images and modify the code to examine the accuracy of those and whether they moved during treatment. Unfortunately, I didn't get a chance during my limited time on this project. Here's a list of my references just using the slides. If you want more references, I have a lot in my thesis, and I'm happy to talk to you about it afterwards. I'd just like to acknowledge Pejman and Martin and Hans. You've all been great supporters and supervisors through this project. Hans specifically wanted to mention Adrian Fitche. I'm sure I messed his name up. He's the service engineer of the Electro Unity. He's done a lot of work on the project too. I'd finally like to thank my family, my wife and kids who've put up with me for the last year of working on this project and have always been a great support. Just wanted to let you know this work has been drafted for submission to an academic paper. We're still working on a draft for that, but hopefully we'll be able to look at submitting that soon. Thank you all. Any questions? Yes.
Question.
Sure.
Thanks so much.
No problem.
Are there any potential improvements to the Phantom which would make it easier to analyse?
Easier to implement? Like to install? I mentioned it was hard to install.
Yeah, or like the circles were a little bit unclear in the image.
Yeah.
Is there anything?
We tried to boost the contrast, I guess, by changing the material, and that didn't really have any effect, which is why I grouped all the results together. There was no noticeable difference. You could look at investigating different materials, I suppose, for the ball bearings to get better contrast. One problem I was noticing, or one problem I believed with the ball bearings being attached so close to the radiation head and so close to the source is that there's going to be a lot more noise from the penumbra, if that makes sense. If there's any scatter going on near the balls that will affect that imaging, it's got a lot more time to spread out, I guess, before it reaches the MVIC. I can't think of any major changes.
Could you make the balls it looks quite large in the image.
if I go back, I've got the dimensions. You could try changing the size. I imagine. Sorry, it's a lot of slides to go through. So we've got 4 mil. I'm not sure why Hans went with that size. Contrast. Yeah, that makes sense. So, yeah, I suppose if you went with a larger ball, perhaps you could get more contrast. You would get less. It would absorb more radiation, so create more contrast. So I suppose it's a trade-off of your positional versus your contrast.
Okay, thanks.
No worries. Any more questions, Jake?
You mentioned that your results were reproducible because you did the measurements twice. Did you present that on there, or did I? Use that?
You can see once they're here, they're all kind of together. Here's the 3 different setups. So these setups go direct. Once I subtract the harmonics of each one, they all have separate harmonics. The data all sort of join together. I presented it as average and standard deviation. So there is a lot of data points within each of those data points. Yeah.
You mentioned that MR imaging, that there are distortions in the image.
Yeah.
Did you do anything to try to correct for those distortions that may have affected
It's a good question. During our imaging, as far as I'm aware, they had the magnets weren't in operation.
Okay.
Because we're using the MVIC panel rather than the MRI imager. We did discuss briefly, quite recently, whether we'd be able to use phantoms that would be visible both to MRI and the MVIC, but that wasn't something we could fit into our project. But it would have been interesting to see if the distortions had an effect. Any more questions?
Any other questions?
Yeah.
So with the accuracy of your coding system, you were saying that you could separate the
Yeah.
Can you try putting intentional errors of known amounts and then see if this is something detected?
That was something I really wanted to implement, if you're thinking of what I'm thinking. One thing I really wanted to do was kind of create my own circle, add random noise, and then do a big sample of like 1,000 or 10,000 of those and see how accurate it was. Unfortunately, I didn't get a chance to do that during my time constraints. But it was something I forgot to mention, but I did think about it at one point. Yes?
It's very interesting to see somebody from WA working on MR-linac.
Yes.
That's great.
Thank you.
Is this work was done in a machine like for research, like you had the field, the magnetic field off, and you're taking all the images, or was in machine it's clinically used?
The machine is clinically used. They've used. I don't know exactly how many patients they've treated. They've released a couple papers I could send to you for their clinical experiences. They've treated quite a few patients, but we did it during QA, like a machine QA, so that when they've turned the machine off and they're taking it apart. So the magnetic field wasn't on, but the big magnetic parts were still in place, but they just weren't switched on.
Are you interested to collaborate with other Australian centres? Or?
Yeah, it would be. I'm not planning on doing PhD at this point. I'm hoping to get into a TAP, but I'm interested in pursuing this further if there's more opportunities. I know Genesis Care over East has an MR and is potentially getting an MR.
I will have a chat with you after that.
Sure.
Thanks, everyone.
Thank you, everyone.